In the previous lecture, we discussed the conditions under which a particle can be accelerated at the reconnecting region. And in this lecture, we will try to see the time scale at which the magnetic field diffuses into the reconnecting region. So let us start with the Ohm's law, that is nothing but J is equal to sigma E plus V cross B by C. So at the reconnecting region, at the reconnecting region, we assume the plasma to be at rest because after the reconnection, the energy is dumped into the plasma and the plasma flows off. But at the time of reconnection, we will assume as the magnetic fields are being diffused into the reconnected region, and the region will assume the plasma to be at rest. So then this term goes off. So I can write J as your sigma E. Now we have the Maxwell's equation. Curl of E is equal to minus 1 by C del B by del T. So now I can substitute in the place of E this. So this is going to become 1 by sigma curl of J is equal to minus 1 by C del B by del T. So now we have another Maxwell's equation, that is your curl of B is equal to 4 pi by C J. I am not going to consider the displacement current because as earlier we are going to assume the scale at which we are dealing, the plasma is neutral and there is no space charge and there is no displacement current. So from here I can substitute this from here into this equation. So what I'm going to get is 1 by C divided by 4 pi sigma into del, so this will be C divided by 4 pi sigma into curl of B, which is equal to minus 1 by C del B by del T, or therefore del B by del T is equal to minus C square by 4 pi sigma into curl of B. Now, as we seen earlier, curl of B is equal to del dot B minus del square B. So this goes off because of Maxwell's equation, del dot B equal to 0. So we are going to have this is equal to minus del square B. So this minus cancels from here. So this term is going to be del square B. So now let us try to do some order of magnitude calculation. So I'm going to write my del B by del T. This is some B by some diffusion time scale at which the magnetic field is diffusing. I'm going to write in terms of the time scale, diffusion time scale, and your del square B can be written as some B by some typical length scale L square. So when I substitute back here, so what I'm going to get is B by tau D is going to be C square 4 pi sigma into B by L square. B cancels off, therefore the tau D is equal to 4 pi sigma L square divided by C square. Well, now let us, C square, this is, So now let us try to put the typical values for the solar flare and see what is the typically your tau D is going to be for a typical solar flare. Okay, for a typical solar flare, your sigma will be 6.7 into 10 to the power of 6 into T to the power of 3 by 2, and your temperature T is 3 into 10 to the power of 6 Kelvin, and your length scale L is 10 to the power of 9 centimeter. So now, interestingly, when you put up these values into this equation, and if you calculate what is your tau d, you will find your tau d will be as an order of 10 to the power of 7 years. And this is a very alarming number because we know the solar flare happens in a few hours. So here the diffusion time scale says, the time scale for the magnetic fields to diffuse into the reconnecting region is typically the order of 10 to the power of 7 years, which is contradictory to what we see in the solar flare. And it was a very serious problem. To an extent, this problem was largely sorted out by the work by Sweet and Parker. So they redesigned this equation, and what they show is that reconnecting the velocity at which the magnetic field gets reintroduced into the reconnecting region is much smaller than this value. So typically the main problem here comes is because of your huge sigma. The plasma, the very high sigma value and the large length scale. So actually, in fact, in the Parker model, you will see the Sweet and Parker model, they say this length scale will not be as large as we have compared the typical scale of the solar flare. This is much smaller than that. So that drastically reduces your diffusion, this time scale of your reconnecting time scales, and we will see about it how this is being achieved in the next lecture. Thank you. Let us consider a flowing fluid, maybe a river or a stream. So, and let the flow be not a supersonic. So now, if I place a barrier in between the flow, this barrier is going to create a difference in the density of the matter on the both sides. Maybe the density will be higher in the upstream region than the downstream region. Not just the density. In fact, all the thermodynamic variable is going to be different in the both upstream and the downstream region. Now, if I remove this barrier, the disturbance cause, which created the thermodynamic change in the thermodynamic conditions, is eventually going to be distributed over the rest of the fluid and will die out slowly. Now, at what is the speed at which the disturbance propagates through the fluid is the speed of sound. Now, let us consider a different situation where the fluid is now flowing at a supersonic speed. And now let me again place a barrier. And this barrier is again going to create a difference in thermodynamic conditions in the upstream and the downstream region. So now if I remove the barrier, now since the fluid is flowing at a speed greater than the speed of sound in the fluid, so the upstream region, the downstream region will not know the condition of the thermodynamic condition of the upstream region, and the upstream region will not know the thermodynamic condition of the downstream region, and the discontinuity which I created, the discontinuity which causes the difference in thermodynamic conditions on the upstream and the downstream region is going to survive and going to remain, and it propagates. And this discontinuity, we call it as a shock or a shock front. Now, if suppose the thermodynamic conditions in the upstream region are extreme compared to the downstream region, as the shock front moves, the upstream region is going to cause a huge devastation on the downstream region. And this is what happens in a nuclear explosion. When a nuclear bomb is exploded, so the shock wave created is going to create a thermodynamical discontinuity between the upstream and the downstream region. And now around the nuclear explosion, the thermodynamic conditions are extreme. So as the shock front moves, it's going to cause enormous devastation all along. So killing millions of lives, destroying the properties, and all the creation painstakingly made by the human, everything will be destroyed, and killing almost every living being which comes on its way. And this devastation is continue till the shock wave exists. Well, so, and that is one of the sad things happens when a nuclear bomb is exploded. Well, there's a one solution. There's only one solution how you can overcome this. And I believe that is the only solution which is exists, and that is thank you.